If I come, it's a liquid.
All right, so we're going to continue. Let's try to get focused, guys. We're going to continue on to chapter 23. There will be a little bit of chapter 3 on the exam. It won't be exhaustive. So anything that we do cover into class up to a day before, you want to make sure that you cover or review for the exam. All right, we've already seen amines a fair amount, but I wanted to get into a little bit of nomenclature, because in this chapter they throw around a lot of nomenclature for amines. So let's take our basic amine. What is this called? Ammonia. Yeah, ammonia. Pretty easy. Oh. And then if we have the conjugate acid of ammonia, what's that called? Ammonium. And then we also just have primary, secondary, and tertiary amines. So let me fill these out, and then we'll add in the appropriate R groups. If we have one R group and two hydrogens, that's primary. If we have two R groups and one hydrogen, that's secondary. And if we have three R groups, that would be tertiary. So primary, secondary, and tertiary amines. So these are our classes of amines, pretty similar to naming for carbons. One new term that they do throw out a lot is alkaloid. Does anybody know what an alkaloid is? What's that?
He said it's a mint.
It's not a mint. That's an alkoid, or what are those called? The altoids? Yeah. Alkoids? Whatever. It's an amine derived from a natural source. So there are a lot of drugs, like, I'll just throw one out. Hopefully none of you guys have done this. Cocaine. Cocaine is an alkaloid. It's a natural product that has an amine functional group off of it. So if you ever hear of an alkaloid, it just means it's a drug with an amine off of it. What's that? A lot of drugs have amines off of them. So an alkaloid just means it's derived from a natural source. All right, let's go over the basic reactivity. Most of this is hopefully a review. Amines are kind of unique because they can act as either a nucleophile or a base, and you guys ran into this on a lot of your sapling problems where people were forgetting that amines are very basic. So if you have something like an acid around, you can form your ammonium salt. And if you've got an electrophile like methyl iodide around, it can also do nucleophilic attack. And we're going to see a lot of this chemistry in this chapter. But it's important to remember that you've got this dual reactivity. It's a very, very good nucleophile, and it's also a very, very good base.
Is it one more than the other, or no?
It depends on a lot of circumstances. So let's say you have a tertiary amine. Is that going to be as good of a nucleophile as a primary amine? It's got more bulk to it, so it won't be as nucleophilic, although it can still act as a nucleophile. All right, so let's go into nomenclature. The nomenclature is really similar to the nomenclature for alcohols. So this should be pretty easy for us. I'll give us a couple of examples. All right, what do you think the first one is called on the far left?
Ethylamine.
Yeah, ethylamine. It's pretty intuitive. What about the next one?
Isopropyl.
Yep. And what about the last one? Yeah, cyclohexylamine.
Close enough. Yeah, you gotta get all fancy.
The key to remember is it is very similar to alcohol naming. So again, you want a number starting closest to the alcohol and then number out from there. But the one caveat is if there are other functional groups besides amines, then they're typically listed as a substituent. So, but if other functional groups are present, the amine is listed as a substituent. Kind of like with our warm-up for the ACS, where we treated the hydroxy group as a substituent because the main chain had a ketone on it. It's similar to with amines. You want to treat an amine as a substituent if there are other functional groups off of there. All right, let's do a practice one. And I'm going to make this trickier. All right, let's name this. Yeah. All right, so let's number our longest chain. Do we number from this end? No. So just like with alcohols, we want to number from the end closest to the amine. 4, 5, 6, 7. So we've got a heptane. And then do we have stereochemistry we should worry about? Yes. So let's take a look at this stereochemistry. What would be the designation for that position? S, because the nitrogen's highest priority, we're going counterclockwise, so this would be S. And then we've got another stereo center.
R.
Yes, this would be an R, so that 4 position is a higher priority than the 6 because it's got more stuff hanging off of it. The 6 would be next highest, and the methyl group would be after that, so this would be an R. So if we were to name this, we would name this as 3S 5R. We always want to name our stereo centers first. And then this would be, 5-methyl 3-heptanone. Oh man, I can't talk. Heptanamine. Oh, yeah, thank you. I'm getting all tongue-tied. Heptanamine. There we go. So the suffix for amines when they're simple amines will just be an amine. All right, let's do another practice one just to see if we're a little rusty. Got to name this. Curveball. You have the book open? I like this one from the book, so I stole it.
Out of the top of my head, just
So a lot of people forget whenever we have benzene rings, we have parent systems off of those benzenes. So what's the parent?
Aniline.
Aniline, right? So we still want to number it, and we want to try to minimize the numbering. So should I go 1, 2, 3? No, we want to go the other way to minimize the numbering. So we go 1, 2, 3, 4, 5, 6. And would we say 5-ethyl or 2-fluoro first? Yeah, because we want to alphabetize it, right? So this would be 5-ethyl, 2-fluoro, aniline. So make sure you remember to include anilines if it is coming off of an aromatic ring. All right, let's do another one that's a little bit trickier. Actually, let me do it like this. We're going to learn a new trick here.
I don't like this game.
But one trick I'll show you guys is if you do have substituents coming off of your amine, you want to name this as N-ethyl, indicating that that ethyl group is coming off of the nitrogen. Same thing with this side.
So would it be in diethyl?
All right, and we want to identify the longest chain. So we've got 1, 2, 3, 4, 5, 6, 7. Do we have stereochemistry? Huh?
No, because they're the same on both sides.
Yeah, if we look at the 4 position, we've got a propyl coming off of each end. So in this case, even though I have it drawn as a wedge, it doesn't matter. There's no stereochemistry. To test you guys. All right, so we've got N diethyl. For heptanamine. So if you do have substituents coming off of your amine, like a secondary or tertiary amine, you should listen. What were you saying, Andy?
I said it's miso, isn't it? That would be the first.
It's just achiral.
Yeah, so
Yeah.
we wouldn't have that.
So meso compounds have stereocenters, but they're superimposable on their mirror image. So this wouldn't be classified as a meso compound. It's just achiral. Mm-hmm.
Thank you.
All right. Let's go on to preparation of amines that we've already seen before. Or actually, I've got a new section, sorry. Preparation of amines. This is all review. The first one is if we have an alkyl halide, so I'll just call this Rx. And we treat this with sodium cyanide. We can substitute off that halogen and get our cyano group installed. But we're not to our amine yet. How would I reduce that cyano group?
Add some water. Or add some acid.
How do we normally reduce things like a carbonyl or? You need a hydride source, right? So hydrides are used to reduce things. So LAH is our typical hydride source that's strong enough to reduce a nitrile. And then you have to do a second step of water to make sure that your amine is protonated. So we're just reducing that triple bond down to a single bond in this case, and you can do that easily with LAH. So I believe we covered that in chapter 20.
Did you do that with any reducing agent at all?
Sodium borohydride's not strong enough. So this is done with LAH. I think there are a couple other hydride sources, but they're not in our book. Yeah. All right, let's go with another older reaction. And I want you guys to figure out what goes over the arrows here. Got a 1 and a 2. No cheating, Eddie. Oops, sorry.
See, now he's looking for it, because you said something.
Now he knows
Wait, don't we have to turn it into the chlorine and then NH3?
Yeah, exactly. So what you need to do first is carboxylic acid is not a good leaving group. So we have to use thionyl chloride, SOCl2, in order to form your acid chloride, and then you need
Excess NH3.
exactly excess NH3. And so we can go to our amide, and then how do we reduce our amide to the amine?
Hydrochloric acid and amine. Is that it?
Not quite. You're thinking of the, I think, Clemenson reduction.
Did that
It
Fisher?
was on our test, you guys. It was one of the boxes on our test.
I'll give you guys a hint. I said, what do we use to reduce an amine to, or an amide to an amine? It's a reduction. Yeah, LAH.
Oh my god.
He's like spoon feeding it to
I
us.
know.
Like, oh.
So we can reduce an amide to an amine.
Wouldn't that just reduce it to an alcohol? And then
In this case, we didn't cover the mechanism, but it will essentially cleave off that carbonyl group. Yeah, we didn't cover that mechanism.
What a Wittig reaction occur?
Wittig reaction? Not quite. So that's normally
Not make it like, oh wait, never mind.
where you. So another approach might be something like the Wolff-Kishner reduction, but that doesn't work well with amides. So typically you just use LAH. All right, let's go on to another old reaction that's review. Oh. I'll be really sad if you guys miss this one.
Oh god, I'm gonna miss it. Just like I did the Texas carbon. Oh, I don't know. HNO3 and H2SO3, right? SO4.
Okay, yeah, let's. You guys are getting pretty rambunctious, so let's try to calm down a little bit. The first step is exactly what we did in lab, right? We nitrated our benzoic acid or our acetophenone, and we had nitric acid, so HNO3 and H2SO4, and that will nitrate a benzene. And then how do we reduce the nitro group?
Oh, that's the one that was on the test. The other one wasn't.
There's a lot of different options here. You can use zinc in hydrochloric acid. You can use iron in hydrochloric acid. You can use tin in hydrochloric acid. You can use tin-2 chloride. You can do hydrogenation. Basically, you can look at these things wrong, and sometimes they'll get reduced as long as they're around acid.
I'll try that.
It's frustrating when you're in a lab environment. These degrade really, really quickly under acidic conditions. I've had that happen to me and had to restart a whole synthesis. All right, the next one I want to do is pretty practical. What reagent would we need? Yeah, methyl iodide. Whoop. And so we can have the nucleophile attack the methyl group, kick off iodide. Will it stay protonated? Yeah, in this case, you can deprotonate it pretty easily because if you've got any excess ammonia around, ammonia can also act as a base. So the ammonia can come and deprotonate it. And we can get to our primary amine. But the problem is, this is really, really hard to isolate. Let me move this down. Why do you think this is hard to isolate?
It'll continue.
Yeah, it's a little bit weird to think about, but we've got a methyl group. Methyl groups, we can think of them as being weakly electron donating. If we're donating electron density into that nitrogen, we've created an even better nucleophile than we started with. So this will continue alkylating uncontrollably. So essentially, this isn't very useful unless you use it to potentially over-alkylate. And what this is called is exhaustive alkylation. Really, this reaction isn't synthetically useful for forming primary amines. So let's put that down. It'll continue over alkylating, and you'll usually end up with a mixture of products that you have to go through and separate one by one. So it's not a very good procedure to use. All right, so now let's cover better techniques for making amines that are more efficient than the ones we've already seen. Is it okay if I flip pages? Okay. So let's look at preparing amines through substitution reactions today, and then we'll cover some new reactions tomorrow that are a little bit different. The first one is called the azide synthesis. And I'll show you guys the overall reaction first. If you start with an alkyl halide, you can throw in sodium azide. And when you do this, you end up with a Zwitter ion with a bunch of nitrogens all lined up. And from here, you've got a couple different routes to get to your amine. You can either hydrogenate it, or you can reduce it using LAH or H2O. Yeah, in this case, why do you think those two nitrogens want to leave?
Gas.
Yeah, you can form gaseous nitrogen. Do you think this is a very safe reaction to do? Yeah, probably not. These reactions can be quite shock sensitive. So if you have your azide and it dries out into a powder and you hit it, it will explode. So oftentimes this route is avoided, but it can be synthetically useful in some cases. Let's go over the mechanism for this, though. So the first step's pretty straightforward. If we have an alkyl halide and we've got sodium azide, the sodium's just a spectator ion. I keep on writing oxygen. There we go. So we've got two negative ends and a positive end. One of these negative ends can come, do a backside attack, and kick off our leaving group. So these are standard SN2 conditions. Can we have a tertiary alkyl halide? No, a tertiary alkyl halide, the backside's too hindered and you can't do an SN2 attack. So you need this to be a relatively exposed electrophile. Silly oxygen. There we go. And now we've got our azide And now let's take a look at what happens when we add in lithium aluminum hydride. The hydride gets delivered to this nitrogen, and then it will kick up a lone pair onto that positively charged nitrogen, or a bonding pair. Okay, so now we're pretty close to being done. The next step, this negatively charged nitrogen will clamp down and then kick off your amine intermediate. So now this nitrogen has two lone pairs and a negative charge. And then we've also bubbled off N2 gas. So you know this reaction is working when it starts to bubble. And then in the next step, we have water. That can act as a proton source, and it can protonate your amine. To your final product. This route is used in some cases just because it's very effective if rudimentary. You just have to be very, very careful when you're doing this because it will sometimes explode if you're not careful. Because of that, people have been trying to find more elegant methods that avoid the shock sensitivity associated with the ZIDs. And the workaround is called the Gabriel synthesis,
Hey.
like the angel.
Yeah, I'm sure it's no angel there.
And so it avoids explosive ZIDs. All right, so let's take a look at the overall mechanism or overall reaction. And then we'll do the mechanism. Oops, sorry. There we go. And this starting material that we're using is called phthalimide. And in the first step of this reaction, we treat it with a base, like potassium hydroxide or sodium hydroxide. And then in the second step, we're going to treat it with an alkyl halide. So I'm going to call this RX. And then in the third step, we're going to treat it with acid. And from this, we can get our amide plus our byproduct, which is this guy. So essentially the nitrogen from the phthalimide gets shoved off and it forms your new amine. So let's take a look at the mechanism. So if we have potassium hydroxide around, what do you think will happen? Yeah, you only really have one acidic nitrogen there. So in this case, it's also between two alpha protons, or sorry, between two carbonyl groups. So it's very, very highly stabilized. So we don't need a very strong base for this to happen. Sodium hydroxide is good enough. So this is acting a little bit like an enolate. And then if we have our alkyl halide around, what do you think can happen?
Substitution.
Yeah, just a simple substitution reaction. This is our standard SN2, so again, we can't have tertiary alkyl halides because they're too hindered, but this will work well in a primary alkyl halide. Whoa, shoot. Okay. And then the next step, we're treating it with acid. And what will acid do to amides?
It'll turn it into a carb. Never mind.
No, you're on the right track.
Okay, I'll turn it into a I'll turn it into ketone.
Turn it into a carboxylic acid, right? We can hydrolyze amides to carboxylic acids. So in this case, each of those groups will get hydrolyzed to a carboxylic acid. And then you will also get your amine out. So this is similar to what we saw in previous chapters. And then the very, very last step is to treat it with base in order to get to our neutral amine. So if you are unfamiliar with the hydrolysis steps, I would encourage you to go back through your notes and review those from the previous chapter. It's pretty similar. You protonate the carbonyl, water adds in, and you have a bunch of proton transfers. So I'm not going to show it all up here. There is one problem, though, with this reaction. This is hydrolysis. And the hydrolysis for amides can actually be quite slow. So there's an alternate route available in order to cleave off your amine. And this is oftentimes preferred. The alternative is once you have your alkylated phthalimide, you can treat it with, sorry guys, with this guy. Does anybody remember what this is called? Hydrazine. If it had an oxygen on there, it would be hydrazone. And if we do this, you can actually speed up the reaction. And it will add in and then pop off your amine really easily, and you don't have to worry about the acid-base workup. So in this case, you trap it as a cyclic ring system. Sorry, this is bugging me. I'm a little OCD on some of my chemical structures. There we go. So oftentimes this is used, you can use hydrazine, it's really gentle. Oftentimes too, when you're doing the Gabriel synthesis, you might have acid-sensitive functional groups in your molecules, so you want to avoid messing with them. You want to leave them be for the time being. All right, so let's do some practice. All right, the first practice problem is I want you to propose a synthesis. And I want you to propose the synthesis using the Gabriel method. So I'll give you guys a minute to work on this. This is pulling from old chemistry. I wanted to review it.
You should use the Gabriel thing?
Mm-hmm. So let's think about retrosynthesis. If we're doing the Gabriel route, where should our halogen be?
Where the Amines too?
So let's do retrosynthesis underneath. We could say, all right, in order to do this, we could have maybe had a bromine on there. How can we get a bromine installed? Yeah, the other route would be radical halogenation, but would that be very good in this case?
That's not.
No, because it's on a primary carbon. That would be pretty hard to do with radical chemistry. So what we could do is start with this guy, and then how could we make our alkene?
Do elimination with a big base after radical halogenation.
Yeah, exactly. And then we could make this pretty easily from radical halogenation because it's on a tertiary carbon. So let's go through and actually add arrows in, or add our reagents in. First step would be Br2 and UV light. That would brominate. Second step, we could add potassium terbutoxide. Third step after that would be anti-Markovnikov addition of our halogen. And then, oh man, I'm running out of room here. Let me slide these down. Then the next part would be to react it with our Gabriel enolate. And I'm going to skip the steps for forming that and just draw it as a negative charge. So we first need to deprotonate that. And then 5 would be our group, or our hydrazine, in order to release the amine there. Let me slide this down too. So we still need to remember all of this old chemistry because it is going to come into play with all of our amine synthesis. All right, let's do one more. I like this example because it's historically relevant, and it's actually in your book. What halogen would you need to start with here?
With the BR or with the...
Yeah, exactly. So you could start with this halogen, and again, you could react this with your Does anybody know the name of this compound on the right?
Far right?
Yeah, far right.
No.
You're close. It doesn't have the methyl group off of it. It's amphetamine.
Oh. Reactivity?
I was looking in your book, and they talk about it a little bit too, and I got really curious. This was first developed in the 30s, and essentially it gives you a high. It messes with your brain chemistry. And the thing that's really interesting with a lot of these drugs is that you've got a phenyl group, and then you've got an ethyl group, and then you've got an amine. So it's called a phenethylamine type of drug. And these oftentimes are involved in the way your brain behaves. So like dopamine and all of these drugs have phenethylamines in them. The Germans developed amphetamine in the 30s, and they realized after doing human testing, it got people really, really high. And so during World War II, they realized that these 18-year-old kids were scared to death of going into battle. So what was the solution? Get them nice and high before going into battle. So this was one of the dark stories of World War II, of essentially before people were sent to go storm the front lines somewhere, they were given amphetamine drugs, and they were scared senseless still, but at least they were high while they were scared senseless, I guess. And then the Germans quickly discontinued it because they realized that by getting people high, they weren't good soldiers anymore. But there are stories of these encounters where these troops were just stoned out of their minds and essentially rushing the front lines and being mowed down by machine guns. And so it's kind of a dark part of our history. Amphetamines are oftentimes over-abused drugs, and so if you are interested in reading about it, it's got a little blurb in your book where you can read about amphetamines. We'll talk a little bit about methamphetamine tomorrow. That's used the synthesis for that is done slightly different, and we'll talk a little bit about Breaking Bad too, just because I like that show. All right, other than that, I'll see you guys in lab.